Hello, everybody. My name is Zhuo, and I'm a PhD student at Norwegian University of Science and Technology, Department of Mechanical and Industrial Engineering. Today, I will be presenting my research topic, thickness effect on the mechanical behavior of PLA specimens fabricated with fused deposition modeling. I would like to take this moment to thank Rakel and my supervisor, Razavi. I couldn't finish this research without assistance from them. So this is the outline for this presentation. First, I will be talking about background and motivation of this research. And then I will be talking about some FDM fabrication process for the specimen we have prepared, and then some experimental procedures and results and discussions, and finally conclusions. So the aim for this research is to investigate the influence of thickness of PLA specimens fabricated via FDM technology on the mechanical properties. Okay, let's talk about a bit about the background of FDM. So fused deposition modeling, which is FDM for short, is one of the most widely used additive manufacturing process in the world. It's a rapid prototyping process that can fabricate physical model generated from CAD automatically without any usage, tooling, or fixtures. So and also FDM is one of the extrusion technologies for 3D printings. And as you can see from this image here, it has a lot of applications, and it consists of a lot of components regarding of environment, filament, hardware, and software. And the motivation for this research is to study the geometry and thickness effect of the FDM printed parts. So based on the literature review, the geometry and thickness of the components can have a very direct influence on the distribution. For example, because of the internal porosities, surface quality, geometrical accuracy, and the residue stresses, which can result in variations of mechanical properties with input geometry. So therefore, it is very important to understand the link between the mechanical property of these components and their geometry and thickness to see whether we can improve the design technique or some applications. So these are the standard dimensions for the test specimens we have chosen. We use the ASTM standard, and we have selected type 1, which have a list of all the dimensions here, as you can see. And this is the fabrication process. For the 3D printer, we have chosen Prusa i3 MK3. It's a very good printer, has a very high resolution. And the filament, we have chosen 3D NAT with the natural color and the 1.75 diameter. And the slicing software we have chosen is the Ultimaker Cura. And this is the dimensions for the specimen we have chosen, and this is the standard ones. As you can see, we have the thickness of 3 millimeters. So in this test, we have 1 millimeter, 3 millimeter, 5 millimeter, and 10 millimeter for thickness. Okay, so this is the fabrication parameters and the process parameters here. So as I mentioned earlier, we have 4 different thickness for the specimen, and these are the cross-sectional area and the gauge length for each specimen. And these are the process parameters we have used to fabricate those specimens. We have made some trials and errors to be able to fabricate those 100% of the infill density, and with the 0.1 relatively smaller layer height to be able to get a good quality specimen. So these are the parameters we have used. And this is the testing machine we have used. So it's called MTS Tensile Test Machine Model 42, and it has the maximum load capacity of 5 kilonewton, and this is very suitable for doing the uniaxial tensile test. And the sampling rate is 10 Hertz, which means we're recording 10 data per second. And the tension rate for this test, we have selected 2 millimeter per minute for the PLA, and the fracture surfaces were also examined with a microscope. And this is how the specimen look after the fracture. As you can see, most of the specimen fracture the position near the gauge length, and some of them get fractured in the middle part, and most of them has a horizontal line for the fracture, and some of them fractured along the raster angles, which in this case we have plus minus 45 alternatively for each layer. And this is how the fracture surfaces look like under the microscope. And as you can see, with the increasing in thickness, there's a tendency to have less defects and voids for the fracture surface. And especially for the 10 millimeter thickness, the fracture surface look really good compared to the rest. So we also used digital image correlation, DIC for short, for analysis. So for subset, we used 29. The subset means the area of the dots which was being tracked by the software for DIC. The larger number it is, the larger area it has, but also it has the larger uncertainty as well. And for step, we selected number 7, which means for every 7 points, the software will take in the average and use the average data to do the measurement and the calculations. And as you can see, the label here, EYY, means the engineering string along Y direction. So as we can play the animation here, but as the time goes by, there is some deformation in multiple middle parts of the specimen, and the propagates to both sides. And then if it reaches at some point, it goes to different color, which means the string is getting larger, and then it will have the largest string showing here, which means this is the area that's most likely to get broken. And these are the methods of calculating Poisson's ratio, and for the DIC we can select one small area somewhere in the middle, and we can do the calculation for the Poisson's ratio. Okay, so these are some images of the DIC and the comparison corresponding to the real specimen. You can see from here the highest stress area is showing in here, and also that's the area for the fraction. And as you can see from this image, multiple areas of the high stress, so which means the specimen could be breaking from here and somewhere in here as well. So there's also a possibility, but the specimen ending up breaking in here. So this is the result for all 4 thickness, and as you can see from this stress and strain plot and the data we have reported in this table, as thickness increase, the ultimate tensile strength also have the tendency to increase, even there is not much difference between the 3 mm one and the 5 mm ones. And also the elongation at failure also increases when the thickness increases. And for that, we can get some conclusions. First, there is a high degree of association between the tensile property and thickness. So in detail, specimens with larger building thickness experience both higher tensile strength and larger elongation failure due to the possible reasons. First, layer quality, because for 3D printing, especially for the FDM, first layer is really important to print and to optimize, and sometimes it can be affected by many other factors. So there's uncertainty in first layer quality. And next is because of the higher number of layers can result in higher temperature gradient in the layers, which can also lead to the increase in the diffusion process between adjacent layers. And this will result in decreasing the void ratio and improving the strength of the bond, which will improve the ultimate tensile strength as the thickness increase. And second, as you can see from the table I showed earlier, Young's modulus is slightly decreased with the increase of the thickness. And there's a possibility that the specimen tend to have less defects and voids per unit volume when thickness increase, according to the image. So for detail, we still need to do the voids and the defects analysis for the fracture surface to confirm this hypothesis. And the standard deviation for the mechanical properties has a tendency to decrease where the thickness increase. So there's a less discrepancy in the data due to the possible reason that uneven temperature distribution on the building plate will have less influence. Because for the specimen fabrication, we have 5 specimens for each case, and we fabricated 5 of them on the same plate, so there might be some uneven temperature distribution on the plate, so that may cause the discrepancy of the data. And when the thickness increase, that the effect of the influence of that is getting smaller. Okay, that's the end of my presentation. Thank you for your attention, and if you have any questions, please contact me.